Okay, welcome everybody to this sessional lecture of the ICM 2022. My name is Jörg Teschner. I'm professor at the University of Hamburg, Department of Mathematics, and I serve here as a moderator. It is my great pleasure to announce the next speaker, which is Professor Yoshiko Ogata. Professor Ogata received her PhD at the University of Tokyo. And after PhD, there were positions as a postdoc at the University of Marseille and the UC Davis. And then she returned to Japan, first at the University of Kyushu. And since 2009, Yoshiko Ogata is holding positions at the University of Tokyo, nowadays as a professor. And in 2021, Professor Ogata has received the Henri Poincaré Prize for groundbreaking work on the mathematical theory of quantum spin systems, in particular on Onsaga reciprocity relations, innovative contributions to the theory of matrix product states and symmetry protected topological phases of infinite chains. And this is also indicating the area in which the talk is going to be situated. So the title of Yoshiko Ogata's talk is going to be Classification of Gapped Ground State Phases in Quantum Spin Systems. The talk was recorded prior to this event, so we will present you a recording. What that means is that we cannot take questions on this talk, so we can now start with the talk proper.
Hello everyone, I'm Yoshiko Ogata from the University of Tokyo. I'd like to thank everyone who gave me this opportunity to talk here today. Needless to say, this is a great honor and pleasure for me. I'd like to talk about classification of gapped ground state phases in quantum spin system. So let me start. This classification problem I would like to talk about. This is a classification problem of certain type of dynamical system, which arises from quantum statistical mechanics. In physics terminology, the system we concern with are called Hamiltonians with gapped ground states. Physically, these gapped ground states represent normal state at absolute zero temperature. And what we would like to do is to investigate the mathematical structure of such normal zero temperature states. So I'd like to start this talk by explaining you the mathematical description of these gapped ground states. Let me start. So let me start from quantum spin system. So quantum spin system is very simple thing. This is just an infinite tensor product of matrix algebra along the lattice. So let D be natural number fixed, and let nu be the spatial dimension. And nu-dimensional quantum spin system is the infinite tensor product of D by D matrices along nu-dimensional lattice. Here, MD indicates matrix algebra of size D, and I denote by the resulting C* algebra by AZ nu and co-nu-dimensional quantum spin system. Now, an element in this sister algebra, two-dimensional quantum spin system, represents a physical observable. This corresponds to random variable in probability theory. Now, in our business, it's important to think about subsystem of the total system. Therefore, I would like to prepare subalgebra corresponding to such subsystem. So let gamma be a subset of two-dimensional lattice, and we do the same thing as we did before. Namely, we tensor D by D matrices along this gamma and obtain some sister algebra A gamma. And this A gamma can be naturally regarded as a subalgebra of total quantum spin system. So we regard it so from now on. And an element in this A gamma, it can be understood that it represents a physical observable localized in gamma. We also say a physical observable which has support in gamma. So this is quantum spin system. Now I would like to introduce something which corresponds to probability measure in probability theory, that is state for us. A state on the two-dimensional quantum spin system is a linear functional on this quantum spin system. So it's a map from the two-dimensional quantum spin system to complex number, satisfying this positivity condition and normalization. So this state, this linear functional, it can be understood as a procedure of taking the expectation value of each physical observable with respect to the given physical state. Now I would like to think about dynamics on our quantum spin system. We would like to think about time evolution. Time evolution is given by so-called sister dynamics. Sister dynamics on a quantum spin system is a group homomorphism from real numbers to automorphism group of two-dimensional quantum spin system. So there can be many different sister dynamics on our quantum spin system. However, it's not that we are interested in any kind of sister dynamics on quantum spin system. We are actually interested in sister dynamics given in some specific manner. And the sister dynamics we are interested in quantum many-body physics are the ones that are given via some local object called interaction. So let me explain what is this local object, interaction. An interaction is a map, phi, from the set of all finite subsets of two-dimensional lattice to our quantum spin system. So for each finite subset X, we assign some element phi X inside of our quantum spin system. And this phi X, it is supposed to represent interaction between spins inside of X. Therefore, it should be self-adjoint and it should be localized in X. So this is the interaction. here is a very simple example of such interaction. So to explain that first, let us prepare matrices labeled by each side of new-dimensional lattice. So let X be self-adjoint D by D matrix for each X in the lattice. And out of that, we define interaction as follows. First, if X contains more than 1 point, then we assign 0. And if X consists of single point X, I will assign this element. This element acts as HX on the X side and acts as identity for any other side. This defines an interaction, the simplest kind. This kind of simplest kind of type of interaction, it is called an on-site interaction. And you will see this on-site interaction later in this talk again. So I introduce interactions, which is a map from finite subset of new-dimensional lattice to quantum spin system satisfying this condition. Now, as I said, we would like to construct sister dynamics out of this interaction. Actually, to make sister dynamics out of interaction, we need to require some additional regularity condition to this interaction. However, today I would like to avoid to go into the detail, and I just mentioned that we need some additional regularity condition to this interaction. In any case, out of such a interaction with suitable regularity, we make sister dynamics as follows. In order to construct dynamics, first we construct something called local Hamiltonian. So let us define local Hamiltonian. Let phi be an interaction and lambda be a finite subset of new-dimensional lattice. We define the local Hamiltonian on this lambda by this formula. Here what we are doing is just collecting, summing up all the interaction term inside of lambda. So this is local Hamiltonian on lambda, and out of this local Hamiltonian, following quantum mechanics, we consider this kind of time evolution and take the lambda to infinity. And if our interaction is regular enough, it is known that this limit exists and defines our sister dynamics on our quantum spin system. So let me summarize the standard setup we have introduced so far. So we are interested in new-dimensional quantum spin system, which is just infinite tensor product of matrix algebra. And physical states are represented by state, which is a positive linear functional on this quantum spin system. And the dynamics time evolution we are interested in is the one sister dynamics given out of some local thing called interaction. So this is a standard setup of quantum statistical mechanics, and this is really a very standard setup, and we can ask many interesting questions about this setup. And among many of such, what we would like to focus on in this talk is ground state. which represent absolute zero temperature system. And here, so let me define ground state mathematically. A tau phi ground state is a state, so positive linear functional, satisfying this condition. Here, delta phi indicate generator of our system dynamics, namely it's given by this derivative, delta phi. So here, what we are requiring is that for all A in the domain of this generator, this inequality should hold. So I would like to give some remark to those who know quantum mechanics. That is as follows. So if we consider this inequality, this condition in finite dimensional quantum mechanical system, then actually you will find that this condition is the same as it is equivalent to our usual definition of ground state in terms of Hamiltonian. So this condition, you can regard it as a generalization of our usual definition of ground state to infinite system. That is one remark. Another remark I would like to make here is that this system dynamics given by interaction, we are interested in such system dynamics. For such system dynamics, actually there always exists a ground state. That is second remark. For our setting, there is always ground state. Now, I am ready to talk about our central object, which is gapped ground state. So here is the definition. We say tau phi ground state omega is gapped if there exists a constant gamma satisfying this condition. Again, here this delta phi is a generator of our dynamics. And here we are requiring that for any A in the domain of generator whose expectation value with respect to the state equals 0 should satisfy this inequality. That is the definition of ground state omega to be gapped. Here is again some remark for those who know quantum mechanics. So again, this condition may look weird for you, but if again, we consider this condition in finite system, then the corresponding condition is that this condition corresponds to that the condition that there is a gap, at least gamma, between the lowest eigenvalue and the second lowest eigenvalue of the Hamiltonian. So again, this can be regarded as a generalization of usual definition of gap system. So that is the definition of gapped ground state. And as I said in the previous slide, for the system dynamics we consider given by interaction, there is always ground state. However, not all of them, not all of the ground states are gapped. And here I would like to declare that we are interested in interaction with gapped ground state. That's what we would like to focus on. Now, this thing we are interested in, this gapped ground state. What kind of states are they? What kind of image we should have about this gapped ground state? As I said in the beginning, the image we should have is that they are normal states, in the sense that it shows exponential decay of correlation functions. So here is some famous theorem by Hastings, and Nahateg-Sims, which says the following. The correlation function of any gap ground state omega of our zeta dynamics decay exponentially first. More precisely, let x and y be finite subsets of no-dimensional lattice. And let A be an observable localized in X, and let B be an observable localized in Y. Now we consider things like this, omega AB minus omega A times omega B, which is covariance in probability theory. Recall that if A and B are independent, with respect to the state omega, then this value is equal to 0 in probability theory. And this value represents how A and B are correlated inside of this omega. So we consider this kind of covariance or correlation function. And the theorem is telling us that this correlation decays exponentially first with respect to the distance between x and y. So here dxy denote distance between x and y, and this correlation function decays exponentially with respect to that. That's what this theorem is telling us. And thinking that this exponential decay is quite fast decay, it means that in this state omega, observable localized far away from each other are almost independent from each other. And in this system, you do not notice things far away from you. Our gap ground state is such a state. In that sense, we can regard this gap ground state to be in normal phase. The correlation decays very fast, and you don't notice things happening far away from you. So it's rather fair to say that we are in normal phase. That kind of image we have about gap ground state. Now, having such an image of gap ground state, I would like to introduce our classification problem of gap ground state phase. So physically, gap ground state is in a normal phase. Now, suppose that there are two interactions in normal phase, and they can be connected via some smooth path inside of this normal phase. It means along this path, nothing critical occurs there in normal phase. So the nothing critical occurs and no phase transition occurs. In this sense, in the sense that we can connect them without experiencing any critical phenomena, we can regard these interactions are essentially the same physically. It's fair to say that interaction which can be connected without facing phase transition to be equivalent. And that is a kind of classification we have. From this point of view, we introduce classification of gap ground state phases as follows. So what we would like to classify is this one, the set of interaction with gap ground states. And we would like to classify them with respect to the following criterion, that is two interactions in this set are equivalent, and I will write like this. If we can connect them smoothly via a path inside of this one. So in other words, if we can connect them smoothly without closing the gap, we say they are equivalent. That is a classification we would like to think about. So, and I said before, two interactions which are equivalent in this criterion can be moved to each other without experiencing physical phase transition. So that is a classification of gapped ground state. That is a basic classification of gapped ground state phases we would like to think about. Sometimes we are interested in systems with some symmetry. And our classification problem also has some version with symmetry. So let me explain about it in this slide. So classification of gapped ground state phases with symmetry. So we introduce the symmetry to the game. In this talk, I'd like to restrict myself to on-site symmetry, which is defined as follows. So let G be a finite group, and let U be a unitary representation of this group G on CD. Here, this CD is a D. D of this CD is a D, which was defining quantum spin system. So let G be finite group, and let U be a unitary representation on CD. And on-site symmetry is given by this formula. Namely, it is just infinite tensor product of adjoint action by U along this new dimensional lattice. And I will denote it by beta in this talk. And an interaction phi is said to be beta invariant if each interaction term are invariant under this beta G, under this on-site symmetry. Interaction phi is beta invariant if each interaction terms are invariant under this symmetry. Now, here is a classification of gapped ground state phases with symmetry. Now, what we would like to classify is beta invariant interaction with gapped ground state. And we would like to classify them with respect to the following classification criterion, that is, two interactions in this set are beta equivalent, and I will write like this with little beta here, if we can connect them smoothly via a path inside of this P beta. So it looks pretty much similar to the classification criterion that we saw in the previous slide, but the difference is now we are requiring the symmetry to be preserved along the path. So this is a classification of gapped ground state phases with symmetry. So I have introduced the classification of gapped ground state with and without symmetry. Now, here is some question. How, having two interactions, how can we say that they are not equivalent with or without symmetry's classification? How we can say they are not equivalent? And to answer this question, natural approach should be to find some invariant of the classification. And in fact, that is what people in the area, including me, are trying to do. And here, what I find to be fun about this and actually this is the main message of this talk, is the following. From such a simple question of classification, which arose from physics, we obtain non-trivial mathematical objects as invariant. So our classification problem is motivated by physics, which is not very natural. We just want to classify normal zero temperature phase. It's a very natural question and simple question. Out of such simple question, we obtain some non-trivial mathematical objects as invariant. I would like to give you two examples of such invariants. And first one is about classification of symmetry protected topological phases in 1 and 2 dimensions. There, we will find group cohomology as an invariant. Second example is classification of certain gap grant phases in 2 dimensions. There, the mathematical object we find is braided sister tensor category. So let me start by the first example, classification of symmetry protected topological phases in 1 and 2 dimensions. So what is this classification of symmetry protected topological phases? In a word, it is a restriction of our classification with symmetry to the trivial phase. What is this trivial phase? In order to explain it, I would like to recall you the on-site interaction, the simplest kind of interaction we saw before. Now, trivial interaction is an on-site interaction with unique gap ground state. Because the interaction is of such a simple form, the corresponding ground state is very simple as well, and it is just infinite tensor product of on-site state. Now recall our classification. Without symmetry, we say that two interactions are equivalent if we can connect them without closing the gap. Now I can define the trivial phase. The trivial phase is the unique equivalence class of this classification without symmetry, including this trivial interaction. So with respect to this classification, there exists exactly one equivalence class which includes all the trivial interaction, and that equivalence class is the trivial phase. So this trivial phase, itself is not that interesting. It's just one equivalence class of this classification, and it's even the simplest one, most boring one, in the sense it includes the most boring type of interaction. However, things get interesting once we introduce the symmetry to the game, and that is the SPT phase, symmetry protected topological phases. So let me formulate this symmetry protected topological phase, SPT phase. So now what we would like to classify is the following thing, this thing, that is we focus on beta invariant interaction with the trivial phase. And we would like to classify this set with respect to our beta equivalence. Namely, two interactions in this set are beta equivalent if we can connect them smoothly via a path inside. So that is a classification problem of SPT, symmetry protected topological phases. And note that in this set, any interaction, any two interactions in this set, they can be connected to each other without closing the gap because both of them belong to trivial phase. However, it can happen that two interactions which can be connected smoothly without closing the gap cannot be any more connected smoothly without closing the gap if we require the symmetry to be preserved along the path. In other words, it may happen that two interactions are equivalent in this classification, but they are not equivalent in this beta equivalence relation. Therefore, this set can split into possibly multiple equivalence classes with respect to this beta equivalence relation. And these resulting equivalence classes are the symmetry protected topological phases, SPT phase. So we are interested in this kind of question. And as I said, we would like to know the invariant. And in 1- and 2-dimensional system, the answer to this question is the following. That is a group cohomology. Namely, in 1-dimensional SPT phases, there is a second group cohomology valued invariant. In 2-dimensional SPT phases, there is third group cohomology valued invariant. So this is an example of derivation of mathematical object, mathematical non-trivial object out of simple classification problem. Now, I would like to explain you very briefly how to find such an invariant. Here is some fact as an input. That is, for an interaction phi in SPT phases, the ground state is unique because it is in the trivial phase. And furthermore, this unique ground state, which I denoted by omega phi, it is beta invariant because the interaction is beta invariant. Now, having this fact as an input, how can we find an invariant? Actually, there is some guiding principle in the analysis of gapped ground state phases. That is the following. If you want to find the invariant, cut the system into two. So we try to follow this guiding principle. So following this guiding principle, we restrict our group action on-site symmetry to the half of the system. Recall that our group action on-site symmetry was given by this form, namely infinite tensor product of adjoint action by U. Now I'm saying that we restrict this group action to half of the system. Namely, in 1-dimensional system, we apply this adjoint of UG only right infinite chain. And in 2-dimensional system, we apply this adjoint of UG only to upper half plane. And we consider such a group action, half version of the group action, and try to investigate its effect on the unique ground state. We consider this kind of group action. Now, as I said in the fact, we know that our unique ground state is invariant under beta G, the total group action. But of course, it is not anymore invariant under this half version of the group action. So this is not equal to the original state in general. This is not equal to the original state in general. There is some excitation caused by this half version of the group action. And this excitation caused by this group action restricted it to the half of the system, namely this one, gives some mathematical object in the GNS representation of omega phi. So recall that GNS representation is defined is something written here. So in general, any state omega over C-star algebra, we can associate a representation of the C-star algebra on the Hilbert space essentially uniquely. And this is called GNS representation. So for any state omega over C-star algebra, we can associate some Hilbert space representation of the C-star algebra we are considering. And this is GNS representation. And coming back to the statement I made in the last slide. So in our unique ground state, it is invariant under total action, but it is not invariant under half of the action. And I was saying that this difference, the excitation caused by half version, gives some mathematical object in the GNS representation of our unique ground state. More precisely, in one dimension, this excitation causes projective representation on our GNS Hilbert space. And it is well known that from projective representation, we can derive second group cohomology. And in two dimensions, the excitation causes cocycle action. So cocycle action is something studied broadly in operator algebra theory, and it is something written here. So it's a map from group G to automorphism group of phonome algebra with a trivial center, satisfying this property, namely, it is almost like group action, but there is some obstacle given by inner automorphism of M. So this is a cocycle action, and I'm saying this excitation caused by half of the group action cause some cocycle action of G on the GNS Hilbert space of our unique group state. And what is well known about cocycle action is that out of that, we can extract some third group cohomology. And that's how we get third group cohomology in two-dimensional system. So let us move to this second example. The second example is about classification of gap ground state in two dimensions. So we consider classification without symmetry now. Now we are interested in two-dimensional gap ground state models, and there are famous models, quantum double model and Levin-Well model, where some string-like low-energy excitation with braiding structure called anyons are observed. And physicists claim that this anyon should be an invariant of the classification. That sounds quite interesting, and we'd like to think about it. But when you think about it, you immediately encounter the following question, that is, what is anyon? So if we want to say something is an invariant of our some classification, then this something has to be defined in a general setting. And the question now we have is, how can we formulate anyon mathematically in general setting? That is some question. But actually for this question, there is a very strong hint that is the following. Anyons are observed in a different context, namely it's observed in algebraic quantum field theory. And in this algebraic quantum field theory, some category called braided sin-star tensor category is derived out of things called superselection sector. And so this braided sin-star tensor category is a category with some braiding structure, so we roughly regard it as anyon. And in AQFT, such anyon is derived out of things called superselection sectors. Then having that, we think like as follows. Although the settings are different from AQFT and our system, it looks reasonable to think of superselection sector for our problem. And in fact, Peter Narkins did analysis of this quantum level model from the point of superselection sector. So let me introduce superselection sector in our setting. Let us recall this GNS representation. So here is the definition. Let omega be a gapped ground state and let H pi be its GNS representation. Then we say a representation rho of quantum spin system is a superselection sector of our gapped ground state if the restriction of rho and this GNS representation pi to some cone area are unitarily equivalent. So by cone here means it's just area of this shape. And we are restricting our representation rho and the GNS representation pi to such a cone area. And we require them to be unitarily equivalent for any cone lambda. So this is the definition of superselection sector, and we were wondering if we can derive a braided C-star tensor category out of such superselection sector. And the answer is yes, under some technical condition. Under some technical condition which is weaker than the one assumed in algebraic quantum field theory, we can derive braided C-star tensor categories out of superselection sectors of gapped ground state in 2 dimensions. And most important thing is that it is an invariant of our classification. So that was the second example, and that's all. And thank you very much for your attention.
Okay, I would like to thank very much Professor Ogata for this beautiful talk, and like to thank the audience for listening, and hereby close this session.